Hi everyone, welcome back. In this lesson, we cover collinearity, also called multi-collinearity, in regression models. Collinearity refers to a situation where two or more predictor variables are highly correlated, meaning one predictor can be linearly predicted from the others with substantial accuracy. Consider the following example, where the regression model is represented by the equation y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon. Here, if we assume x2 is perfectly correlated with x1, then we can represent x2 as alpha times x1 for some non-zero constant alpha. Substituting x2 equals alpha x1 into the model, we get a form of the model that is only dependent on x1. Here is a dataset with 5 observations. Notice that x2 equals 2 times x1 for every row. When fitting the OLS model with beta 0 equal to 0, any combination of beta 1 hat and beta 2 hat satisfying beta 1 plus 2 beta 2 equals 3 fits the data equally well. For example, these 4 combinations all yield identical predictions. We cannot uniquely determine beta 1 hat and beta 2 hat. We only know that their combination must satisfy this constraint. The presence of collinearity has the following effects on the regression model. For a model with collinearity, R² can still be very high, or even 100%, indicating a strong overall fit. However, individual coefficients may not have a unique interpretation because many different coefficient sets can produce the same fitted values. Fortunately, the overall error variance estimates in f-tests remain valid, so you can still trust tests about the overall quality of the model. Collinearity increases the standard errors of individual regression coefficients, which results in smaller t-ratios and makes it harder to determine whether a coefficient is significantly different from 0. Even if a predictor is genuinely important, collinearity can mask its significance. The coefficient standard errors might be so large that neither predictor appears to be significant, even though they both strongly influence the response variable. The variance inflation factor can be used to quantify the severity of collinearity. The first step to detecting collinearity is to create a scatterplot matrix. It lets you visually inspect the pairwise relationships among predictors. Next, we can use the VIF to quantify the severity of collinearity. Consider explanatory variables x1 through xp. To calculate the VIF, for each variable xj, first run a regression using xj as the response variable and all other x's as explanatory variables. Let r² sub j be the coefficient of determination from that regression. The VIF for xj is then defined as 1 divided by 1 minus r² sub j. A larger r² sub j results in a larger VIF sub j, indicating greater collinearity between xj and the other predictors. The VIF is preferred over r² sub j because of its direct relationship to the standard errors of the regression coefficients. The standard error of b sub j equals s times the square root of VIF sub j divided by s sub xj times the square root of n minus 1, where s is the residual standard deviation and s sub xj is the sample standard deviation of the jth variable. From this equation, we can see that a larger VIF sub j directly inflates the standard error of the corresponding coefficient b sub j. As a rule of thumb, when VIF sub j exceeds 10, corresponding to r² sub j greater than 90%, severe collinearity exists and corrective action is needed. In t-tests, variables may appear statistically insignificant for 3 reasons. The first reason is natural variation, measured by a large residual standard deviation s. To address it, reduce variability where possible. The second source is high collinearity, which makes it difficult to distinguish individual variable effects. To address it, we design the sample to reduce redundancy among predictors. The third source is a small sample size n, which leads to larger standard errors. To address it, increase the sample size. Now let's discuss strategies for addressing collinearity. For collinearity, we are concerned only with linear relationships between variables. Nonlinear relationships, such as between x1 and x2 in this example, do not pose the same issues because they are inherently nonlinear. However, if a nonlinear relationship appears almost linear within the range of the data being sampled, it can still lead to collinearity problems. 3 strategies for addressing collinearity include the following. The first strategy is centering variables. Subtract the mean and divide by the standard deviation, especially when variables use very different scales. The second strategy is simply acknowledging the existence of collinearity. In observational business or economic data, collinearity may be unavoidable. The third strategy is to use auxiliary or transformed variables, or remove redundant predictors when substitution is not practical. Even when an explanatory variable is nearly a linear combination of the others, it can still provide valuable information. A suppressor variable is an explanatory variable in a regression model that increases the predictive validity of other variables when included in the model. Consider one response variable, y, and 2 explanatory variables, x1 and x2, where x1 and x2 are highly correlated. Running individual regression models, x1 yields an r-squared of 3.5%, and x2 yields an r-squared of 0.04%. However, when both x1 and x2 are included in the model, the r-squared jumps to 80.7%. This significant rise shows that, despite their high correlation, x1 and x2 complement each other and provide valuable, non-redundant information about y. When x2 is added to a model that already contains x1, x2 is the suppressor variable, as it dramatically increases r-squared. Likewise, when x1 is added to a model containing x2, x1 is the suppressor variable. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.